Welcome back. It's a delight to be here with you. Recall that we're working through the fundamentals of GPS, really the fundamentals that apply to all the satellite navigation systems. We've talked about the satellites themselves. We've talked about the dual threads of information that come down from the satellites, the nav message, the nav signals. We've talked about pseudo-ranging, that fundamental building block, that essential measurement made by the receivers. And now we have enough information to have a first discussion about how well does this all perform. We have shown this view graph before. These are the four essential elements associated with the measurement from one satellite. And so the satellite is that red clock shown in the upper right. It needs to transmit on time. We need to know the exact location of the satellite at the time of transmission. We need to have a very good notion of what's the speed of the wave, and we have to do a good job measuring the arrival time down at the user. And we talk about nominal accuracy. By nominal accuracy, we mean that all four of those functions are going reasonably well. They're in their usual state. Time of transmission is being controlled to about 1/1000th of a second. Satellite location is being estimated and transmitted to better than a meter. The speed of the wave might have some error in it, but that error results only in about a 1 meter error in the measurement of range. The time of arrival is being made to within a nanosecond or so. In this case, the figure that you see there is in force. And please take a close look. It's really worth our study. What we have there are 8 hours worth of data. And the dashed curve is the vertical error. And notice the scale on the left, it goes from -100 meters up to +100 meters. So that is the scale that was appropriate prior to the year 2000. We'll come back to that. The solid curve is the horizontal error. So the horizontal error is measured as the length of the vector from the true location to the estimated location. So it's always positive. The vertical error, being just one dimension, is just the error up or down away from the true location in the vertical. So that, the dashed curve can be both positive and negative, whereas the solid curve is always positive. Notice also that the dashed curve, the vertical errors, are larger than the horizontal errors. That's because GPS, in addition to requiring good measurements for each satellite in view, requires that you have a good spread of satellites in view. It would not do much good to measure the range to a single cluster of satellites very close to each other. And so we like them spread out. Now for lateral, for horizontal, that's not too tough because we can spread the satellites across the upper hemisphere relative to the user. But there's nothing we can do to put a satellite below the user. The Earth is opaque to satellite signals, to GPS signals, and so the satellites on the other side of the Earth, they're there, but we take no benefit of them at any given position fixing time and operation. So the dashed curve will always be bigger than the solid curve, larger. The other critical thing about this view graph is that at 4 o'clock, universal time coordinate, on this day in 2000, Dr. Sherman Low, measured this dramatic improvement in GPS accuracy. Notice that the position errors went from plus or minus 50 meters down to around plus or minus 5 meters. Up until this time, up until that event at 4 o'clock UTC, the GPS satellite signals had been intentionally degraded. The Department of Defense was concerned about making the full capability of GPS available to civilians worldwide. And so they had intentionally jittered the clock. In other words, the information that described the time of transmission of the signal from the satellites was not quite correct. And it was a time-varying error that was introduced there. at this time, in 2000, that capability was turned off. And by the way, it has been forever turned off. And current satellites don't even have the capability to do that. And so now we get down into this nice regime with the true civil accuracy of GPS in evidence. And we're looking at errors here of around 5 meters or so. Still slightly greater in the vertical than in the horizontal, but the performance is clear. Here's another look. It does not show error versus time. Think of this as a top view. You're looking down at the receiver, and in both cases, the receiver is located right here at the origin. And the points scattered out from that origin are individual position fixes made by the user equipment. And so they're scattered around, and for that reason, both of these plots are called scattered plots. And the one on the left is for a rather inexpensive receiver, and notice that the error in both axes is from -10 to +10. Over here with the more expensive receiver, we're measuring from -5 to +5. So everything on the right suggests that that receiver is about twice as good as the receiver on the left. It's certainly more expensive. Both of these are taken after the time of that intentional clock degradation. So we're now in the more intrinsic high performance period of GPS. Now, the scatter plot on the left is representative of maybe a $5 receiver, and the one on the right probably around $500, something like that. Importantly, GPS also measures automatically velocity. We haven't talked about that measurement yet, but it's based on the Doppler shift. So those carriers coming from all of the satellites in view, not only do they carry the information about the code and enable the receiver to measure the arrival time of the code, the frequency of the carriers shifts up a little bit when the range between the satellite and the user is closing, and shifts down a little bit when that range is opening. Given that we know the satellite trajectory very precisely, we can allocate that part of that upshift or downshift to satellite motion, and confidently know that that part that remains is entirely due to user motion. So please bear in mind that GPS has this capability to intrinsically and automatically measure not only range, but range rate. And range translates into position of the user, and range rate translates into the velocity of the user. Note that the performance here is very good in terms of velocity. And if we look at the scatter, once again organized by selective availability off or selective availability on, selective availability was the name of this intentional degradation that we talked about earlier. I'll just put it here for you. So with SA off, in other words, modern times, we can measure velocity in north and east down to around 0.2, my guess, 0.2 meters per second. In other words, 20 centimeters per second. That concludes our first look at performance. When we come back, we'll begin a module called number 2, and it will have a much deeper look at what goes on in the receiver. We'll move away from our simple description of pseudoranges. We'll go one layer deeper, talk about how to linearize those equations, and really implement the navigation algorithm on the user receivers. And we'll also use that linear set of equations to formalize how to characterize performance. In other words, we'll come up with an analysis that comes behind these results you've seen in snippet 1.10. Thank you.